This video is brought to you by mywayteaching.com.
In this part, let us study second law of thermodynamics. Okay. See, the first law of thermodynamics is the principle of conservation of energy, isn't it? And even common experience, it shows that there are many conceivable processes that are perfectly allowed by the first law and yet are never observed. For example, you consider nobody has ever seen a book lying on a table jumping to a height by itself. Have you? No, right? But such a thing would be possible if the principle of conservation of energy were the only restriction. The table could cool spontaneously, converting some of its internal energy into an equal amount of mechanical energy of the book, which would then hop to a height with a potential energy which is okay, potential energy which would hop to a height with potential energy which is equal to the mechanical energy it acquired. But this never happens. Some additional basic principle of nature forbids all these above processes, even though it satisfies the energy of conservation principle. So, this principle, which disallows many phenomena consistent with the first law of thermodynamics, is known as second law of thermodynamics. Okay, and second law of thermodynamics gives a fundamental limitation to the efficiency of heat engine and the coefficient of performance of a refrigerator. So that limitation is given by the second law of thermodynamics. In simple terms, it says that efficiency of heat engine can never be unity. Is that true? Yes, it is true. Efficiency can never be 100%. So, efficiency of refrigerator can never be unity. So, heat released to the cold reservoir can never be made zero. For a refrigerator, the second law says that the coefficient of performance can never be infinite. One more thing, what it says is coefficient of performance it can never be infinite. This implies that the external work can never be zero. The following two statements, one due to the next part we are going to see what are those two statements. Kelvin and Planck denying the possibility of a perfect heat engine, and another due to Clausius statement denying the possibility of a perfect refrigerator or heat pump. So you can see those statements here. So the first one is Kelvin Planck statement. What he says: no process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of the heat into work. So it is not possible to convert completely heat into work. That is what this Kelvin Planck statement says. Okay. And the second statement, that is a Clausius statement: no process is possible whose sole result is the transfer. Okay, it can be proved that the two statements above are completely equivalent. So, no process is possible whose sole result is the transfer of heat from colder object to a hotter object. Okay, now let us study about the reversible and irreversible processes. What are these reversible processes and what are these irreversible processes? You just imagine some process in which a thermodynamic system goes from the initial state I to the final state F. Okay, just imagine a thermodynamic process in which a process goes from the initial state I to the final state F. So during the process, the system absorbs heat Q from the surroundings and performs work W on the surroundings. So can we reverse this process and bring both the system and surroundings to their initial state with no other effect anywhere? Is that possible? See, most processes in nature, this is not possible. The spontaneous processes of nature are irreversible. Several examples we can consider. See, the base of a vessel on an oven is hotter than its other parts. You agree, right? So, when the vessel is removed, heat is transferred from the base to the other parts, bringing the vessel to a uniform temperature. The process cannot be reversed in this case. A part of the vessel will not get cooler spontaneously and warm up the base. So it will violate the second law of thermodynamics if it did. So the free expansion of a gas is again irreversible. Isn't it the free expansion of the gas? The con- combustion reaction of a mixture of petrol and air which are ignited by the spark. Again, that is also a spontaneous process which is irreversible. Cooking gas leaking from a gas cylinder in the kitchen, it diffuses to the entire room. The diffusion process will not spontaneously reverse and bring the gas back to the cylinder. So, the stirring of a liquid in thermal contact with a reservoir will convert the work done into heat, increasing the internal energy of the reservoir. So again there the process cannot be reversed. Otherwise it would amount to conversion of heat entirely into work violating the second law. So irreversibility is a rule rather than exception in nature. See why this irreversibility it exists or from how it arises. See this irreversibility it arises mainly because of two causes. Okay. One is many processes, for example, like free expansion or explosive chemical reaction, you can take. They take the system to non equilibrium states. That is the one reason for irreversibility. And the another reason is most processes involve friction, viscosity, and other dissipative effects. For example, moving body coming to a stop and then losing its mechanical energy as heat to the floor and the body, and in case of a rotating blade in a liquid coming to stop due to viscosity and losing its mechanical energy with the corresponding gain in the internal energy of the liquid. So this is the second reason. So most processes, they involve friction, viscosity, since these dissipative effects are present everywhere and even it can be minimized but not fully eliminated. So most of the processes that we deal in our surroundings, they are irreversible, and even all spontaneous processes are also irreversible, isn't it? See, a thermodynamic process, that is which changes its state from initial state to final state. You just consider a thermodynamic process. Initial state is given by I and the final state is given by F. Okay, is reversible if the process can be turned back such that both the system as well as surroundings return to their original states. One, which means if it is already in the state F, this process we can call it as a reversible process. Again, if it get back to the state I, that is initial state, with no other change anywhere else in the universe. A reversible process is an idealized notion. A process is reversible only if it is quasi static and there are no dissipative effects. In this case, only a process can become reversible. Okay. If the process is quasi static and if there are no dissipative effects, then only we can say a process is reversible. For example, a quasi-static isothermal expansion you can consider of an ideal gas in a cylinder which is fitted with a frictionless movable piston. That is the simple example for the reversible process. Okay. So reversibility, it is the basic concept in thermodynamics. See, because one of the concerns of thermodynamics is the efficiency with which heat can be converted into work. So that is the basic concern of this thermodynamics. Okay. The second law of thermodynamics rules out the possibility of a perfect heat engine with 100% efficiency, which means no heat engine is having 100% efficiency. So the heat engine cannot have that unity efficiency value. So what is the highest efficiency possible for a heat engine which is working between two reservoirs at temperature T1 and T2? If you think of this question, then it turns out that a heat engine based on idealized reversible process achieves the highest efficiency possible. All the other engines involving irreversibility in any way have lower than this limiting efficiency. Okay.